Hey, what's up, guys? This is Chung here again. So, so today let's take a look at the second last problem of this week's weekly contest, number 1674, minimum moves to make array complementary. I mean, this one is a really hard problem. In my opinion, I think it's even more difficult than the last problem. So you're given like an integer array nums of even number of integers and an integer limits. So in one move, you can replace any integer from the nums with another integer between 1 and the limit and inclusive. And then it defines the complementary. So complementary is the is for all the pairs with the nums I plus nums n minus 1 minus I equals to the same sum. So for example, the rate this one is complementary because for all the indices, they're all equal to 5. And then it asks you to return the minimum number of the moves required to make this num complementary. So here we have some examples here, right? I mean, so for example, the in example 1 here. So 1 plus 3 equals to 4, and then 2 plus 6 equals 2 plus 4 equals to 6. So the sum we have is 4 and 6. And the limit is 4, which means that we can simply make uh, we can make this 1 equals to 3. We can change this 1 to 3 because 3 is in the range of 4, so that both pairs have the same sum, which is 6, right? And example 2 here, right? So I mean the first pair sum is 2, the second pair is 4. But in this case, we cannot make 1. So the optimal solution is the way is to make this 1 to 3. That will only be 1. But since we have this limit here, that's why we have to make either make this 2 becomes 1 or this 2 ones becomes 2, right? And the last one, this is already complementary. That's why the limit is 2. That's why the output is 0, which means we don't need to do anything. So at the first glance, right, I mean, we have a minimum. When you see a minimum, of course, you will try to solve it with different approaches. First one is like what? Maybe binary search. Maybe you try binary search, but can we solve this problem with binary search? Mm, Probably not, because for binary search, let's say we're assuming we are given like uh, a number of moves. Let's say given number of moves m. Can we find the helper functions to help us, I mean, decrease the search range, right? So even given like the number of moves, which means that can we within m moves, can we make these numbers a complementary, right? So for that, we still need to figure out which sum we need to choose. Basically, which is the target sum for all the pairs, right? So that's not going to help us. So the binary search is not an option. And second one is what's the DP? But for this one, obviously there's no DP. It's not a DP related problem because there's no state transition function, right? Because it's not a sequence by sequence. It's everything all the pairs should go to the same sum, right? I mean, even if you try to solve this one with DP, you're gonna be like the DPI, right? So the DPI, which means that is the current sum, right? What's the what's the minimum moves to make all the pairs complementary? I mean, with this given given sum here, right? And from here and then basically we will try to figure out like state transition function with dp I minus one, something like that. But there's no correlation between a different sum, right? So and dp is not an option either. And then what else, right? So I mean maybe the sliding window or the greedy, but none of them works. So if none of those approaches works, what shall we do, right? I mean, then most likely we have to try something different. I mean, which means we have to try something very basic. It's more like a brute force plus optimizations, which means we will basically try all the possible sum within a range, right? And uh, and then we'll but for that, if we but so the range of the sum will be what? So we start from two because the uh, the numbers we have two numbers, so the minimum for each number is one, right? And how about the maximum? The maximum is basically the maximum of the sum, right? So this is the range, and we want to try each of the range, each of the sum here within the range here, and we'll see which sum can give us the minimum number. But how can we know the minimum number, right? Okay, so from here onwards, let's go back to look at the one of the constraints here. So notice here that limit is greater than any of the numbers here, right? So which means that what does it mean? It means that and so it means that for each of the pairs, right? For each of the pairs, actually the maximum movements we need to do is that actually that one it doesn't really matter with this limit if it's greater or equal than the nums. The you know the worst case scenario, right, is what? It's the for each of the pairs we can always change those two pairs from a number a and b to one and one, right? So which means that in that case, basically all the numbers becomes all one, so that each pair, so the total sum it will be two by changing this a and b to one. So it means that we need at most two moves per each pairs to make them a complementary array. That's going to be the worst case scenario. And then let's keep thinking, right? So when can we make one move to make them to a target sum, right? So what's the range? What's the range for one move or zero move, right? Let's say so we have this one, 3, and 4, right? So let's say a is 1, b is 3, and the limit is 4. So what's going to be the range for this pair? What's the sum range, right? The total range for this pair to can only make one move, right? So the of course the smallest is what? It is 2, right? Because 2 is always the smallest. Between 2 and what? So because for the smallest range we change mm, actually this is not a good example. Let's say we have 3 and 5 and the limit is 4. Okay. So for this case, right? So what's going to be the smallest range, right? The smallest sum that we can make one move to make that to make that total. basically we pick the biggest, we pick which one is bigger, and then we change this one to 1, right? So basically, the smallest sum we have here is 4, which means as long as the sum is between 4 and what? 4 and 9, right? It's 4 and 9, then we can only make this one move. Why is that? Okay, so go back to here, right? So the smallest we have is 4. That's kind of obvious, right? Because the smallest we can get by changing one number within range 1 and 4 is we pick the bigger numbers and we change it to 1. So after doing that, so the total will be 1 plus 3, which is 4. And how about the uh, the how about the right side? Okay, sorry. So since here, we have, oops, 5, 3, and the limit. Sorry, the limit will be let's say the limit is 6. Okay, because the limit is always greater than any of the numbers. So that's why the minimum is 4. How about the maximum? The maximum is what we basically pick whichever is smaller, and then we plus the limit, which is 3 plus 6 is 9. Sorry, it's not the. I'm sorry. So is the we pick the smaller numbers, and then we change the smaller number to 6. So now we have 3 equals to 6. So the upper bound is 5 plus 6, which is 11. So now we have a range here, right? Which means that from 4 to 11, as long as the sum, the total, the target sum, or total target, the total is within 4 and 11, then we only need one move to make this number A and B to equal to this sum, right? And for each of the pairs, given two numbers plus a limit, we can have like this range here. So now we have a range for each of the pairs, right? And we have a limit. We have the range of the sum, and we just need to find basically, So now the problem comes down. We have a range here. We have different range, right? Some of them might be overlapping to each other, Some of them are not, right? So we have this kind of range here. Now we want to find what we're looking for here. We're looking for like the most overlapped range because anything outside of this range, any place outside this range, we will need like we'll need two moves for each of the pairs. So which means in total we have n moves, right? This is the worst case scenario because the n is the length of nums, right? So every time when we enter like a range here, it means that we can do a n minus 1 because now we have a if let's say if the sum is right here, right? And then we know, okay, so now we can remove we can use one last move to make all the numbers complementary, right? With this current sum. And if we keep moving, if we are right here, then okay, so we have entered two ranges, right? And then the n can do a minus 1 again, right? And here, if we're at here, right? And then okay, so now we have a 3 overlapped range here. So now we can do it as minus decrease the total n by 1 again, right? Same thing when we exit this range here. So if we are at here, if we're at here, we're outside of the first range. That's why we have to do a plus 1. no, sorry, not plus one. So now we can only do a n minus two, right? Same thing, and then we just keep going forward. So the way we're doing this kind of line sweeping thing is because, let's say we have a range S, and if we're trying to use that, if we try to fix each of the sum here, right, the sum, and then with others of those ranges, if we try to see, okay, how many, if this sum, how many ranges can this sum falls in, right? If we do it in that brute force way, it's going to be a O(n) square time complexity, and with this the constraint 10 to the power of 5, that would TLE. So that we have to use this kind of line sweeping techniques to improve this O(n) squared to a O(n), right? To O(n). Basically, every time, when we enter like a range, we do a -1, right? So here is also -1, and when we are outside of the range, we do a +1. Here we do a +1. We also do a +1. And yeah, so then we can just using this n as a base, and then we'll see how many numbers, how many less movements we can make, right? While trying all the possible sums. And that's the basic idea here. Okay. So so for the codings, right? So I have a sum equals to default of dictionary. So I'm going to use two dictionary to store mm, the diff, right? So I'm going to have a diff here. So default dictionary integer. So and then I have an n here, length of the nums, right? So first, let's try to create those ranges, right? So like I said, so for the ranges, I'm not going to store those ranges. So like I said, I'm only going to mark that -1 or +1 on this 1D line here, so that later on I can sweep this all the points from left to right. So here we have -1, -1, +1, +1, those kind of stuff, right? Because if we do a range, if we store them with a start and end range here, right, and then for with a given sum, right, we have to compare with each of the range pairs. That's going to be too slow for us. So now we have I in range and n divided by 2, right? Since we are only need those half of the sides because we are looking for a pair. So we have a right equals to nums I, and then we have a b equals to nums n minus I minus 1, right? So that's two numbers. And then let's say I need a minimum of them, which is the minimum of a dot b, right? And then I need a maximum of them as well, equals to max a and b. So, and the left, right? So for this kind of range, like I said, the left is what? The left is equal to the minimum plus 1, right? So which one is smaller? We use that plus the other one. We change the bigger one to 1. That's going to be the left boundaries. And the right boundaries is on the other side, right? It's going to be the maximum, right, plus the limit, right? So to calculate the right boundaries, we we change the smaller number to the biggest to the limit numbers, and then we plus the maximum. That's going to be the right boundaries. And then we have a diff, right? So now we can mark the diff. So the left boundaries, every time when we have a left, we'll do a -1. Okay. And when we're outside of the right boundaries, but we have to do a right +1, and then we do a +1 because because the left and the right, they're both inclusive. They're both inclusive. That's why whenever we're at the right +1, then we know, okay, we are outside of that boundary, that range. And another thing we also need to do is that's why I use the sum here because we also here we're only considering the one move case, but there's also like a zero move case, which is the whenever the sum is equal to the same of the A and B, then we don't need anything. We can just do we only need to we just need to do zero moves. That's why I'm also going to count the total the sum right of with the, the count for all the sum so that later on I can subtract this number from our final loop here. Now the so we have what? Mm, so the answer will be system dot max size, right? That's gonna starting point and let's say we have so we have a current. Let's say the current is n, right? So I mean n is our starting point. Basically that's gonna be our worst case scenario, right? And then for s that's gonna be the sum, right? For sum in the range of like I said 2 to the max sum, right? Max sum plus 1. That's it, our sum range. And current plus what? Plus diff s. So every time when we have a new sum here, we update the current. Basically, we'll see how many less or how many more operations we need here. And then after this one, we'll just update the answer, the minimum of the answer, right? Dot current. But don't forget to minus these two things because for this current one, right? I mean, it also includes it not only includes the one move case, but it also includes the zero move case. That's why we have to subtract those zero move case from this current so that this current will be the actual accurate. Because let's say for example here we have for minus one move since we only marks the left and right side. So this minus one this is a minus one, it's only representing minus one case. But if the sums is equal to to the to this a and b, besides minus one, we also need to do another minus two because for those like the pairs, actually we should do a minus two case, right? But here we only doing minus one. That's why for those pairs we have to do another minus one. Okay. Yeah, and then in the end, we simply return the answer. Yeah, I think that's it because we're maintaining these things, right? We're trying to get the minimum for each of the sum. And the sum is simply like accumulating basically the difference by doing a line sweeping of this 1D line here. And then if I do a sum here, okay, okay, nums. Hmm, why it's taking so long? All right, accept it, submit. All right, so it's accepted. I mean, so I think the time complexity for this one is pretty straightforward, right? We have a on here, we have for loop here, which is on, and then we have another. This is on. This is the actually this is the maximum of the sum. So basically, we have a O of what is it? It's a maximum of n or the max sum, right? whichever is bigger, then that's gonna be our the time complexity, right? And the space complexity is of course is O of n, right? Because of this two dictionary here. Yeah, I mean that's basically the intuition for this problem, you know. So I think what's make this one a hard problem is the way we're solving this kind of solving this range problem, and basically we're using like a line sweeping by mark the starting point and ending point on this 1D array here. So we have -1, and this kind of technique is not a very common one. And if you don't know, or if you haven't seen this kind of techniques, I think it will be really hard to solve these problems by yourself unless you have previously seen or know there's like this kind of technique that you can use to mark the range, right? So that's the first thing. And the second thing is that's one of the prerequisites, which means that you have to find out the range, right? You have to be able to find the range to make one move, and anything that outside of that range will make two moves. And then from there you can have like a base, you can have a base here, right? And then for each, and then you can do the line sweeping by every time when you enter like a range, you do a -1, and every time when you're outside of the range, you do a +1. And of course, you also need to maintain this zero case. Yeah, anyway, so basically a few small techniques combined together, you know, so and then you can solve this problem. Anyway, it's a cool problem, which is also a hard one. And I hope you guys enjoy watching this video. Okay, thank you so much, guys, and stay tuned. See you guys soon. Bye bye.